What's good, everyone? Welcome back to another project by the Gapplebees. This slideshow will be on the electronic properties of our given semiconductors, gallium and phosphorus. I'm James, and I'll be joined by Grace and Karloot shortly. Enjoy.
The first topic we'll discuss is the electron configurations of our four elements, starting with aluminum. Simply put, electron configuration describes how electrons are distributed around an atom's nucleus. Electrons occupy specific regions called orbitals, which represent the areas where electrons are most likely to be found. These orbitals are grouped into sublevels S, P, D, and F, each with a distinct shape and energy level. You can see representations of these shapes in these orbitals in the top left corner of our slide. Each type of orbital can hold a specific maximum number of electrons. The s orbital holds up to 2 electrons, the p orbital holds up to 6, the d orbital holds up to 10, and the f orbital can hold up to 14 electrons. This organization is critical to understanding the periodic table, which is structured to reflect how electrons fill these orbitals. If you look closely at the periodic table on the slide, you'll notice it's divided into blocks. The blue region, S block, represents elements filling s orbitals. The green region, the p block, corresponds to elements filling p orbitals. The yellow region is the d block, and the cyan region is the f block. To represent electron configurations, we use a shorthand notation that specifies the energy level, or row of the periodic table, the type of orbital, and the number of electrons in that orbital as a superscript. For example, 1s2 tells us that the first energy level's s orbital contains 2 electrons. As we move across the periodic table, we can follow this pattern to determine how many electrons fill each orbital step by step. The periodic table itself is a powerful tool for understanding electron configurations. Each row of the table, except for the d block elements, represents a new energy level. Elements within the same column or group share the same number of valence electrons, which are the electrons in the outermost shell. These valence electrons determine how elements behave chemically and how they bond with other atoms. If we start at hydrogen, the first element, and read across the table row by row, we see that each element adds one more electron to its configuration. This systematic buildup reflects the way electrons fill orbitals according to 3 key principles. The first, electrons fill the lowest energy orbitals first. Second, each orbital holds a maximum of 2 electrons with opposite spins. And third, electrons fill orbitals of the same energy, like p or d, singly before pairing up. Let's apply this to aluminum, the first element we're discussing today. Aluminum is the 13th element in the periodic table, meaning it has 13 electrons. To determine its electron configuration, we follow the order of orbital filling. The first 2 electrons go in the 1s orbital, giving us 1s2. The next 2 electrons fill the 2s orbital, 2s2. Then 6 electrons fill the 2p orbital, 2p6. That brings us to 10 electrons so far. The next 2 fill the 3s orbital, 3s2, and the final electron goes into the 3p orbital, giving us 3p1. So the complete electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1, or in shorthand, Ne 3s2, 3p1. Here, Ne represents the electron configuration of the noble gas neon, which simplifies the notation by focusing on the outermost electrons. This configuration tells us that aluminum has 3 valence electrons in the 3s and 3p orbitals. Next, we'll look at the other elements and see how their electron configurations compare. Next, we'll look at phosphorus. Phosphorus is the 15th element, meaning that it has 15 electrons. If we arrange these electrons how we discussed in the previous slide, we will see that the electron configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, or in other words, neon 3s2, 3p3. Now if we look at the 3p sublevel on the bottom right of our slide, right here, we'll see that each orbital is filled with a single electron. That is consistent with the third key principle that we learned. Electrons fill orbitals of the same energy, like p or d, singly before pairing up. Now we'll look at titanium. Titanium is the 22nd element with 22 electrons. When we arrange these electrons into orbitals, we get the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, or in other words, argon 3d2, 4s2. Lastly, we have gallium, our largest element with 31 electrons. The electron configuration for gallium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, or in other words, argon 3d10, 4s2, 4p1.
In this slide, we discuss how to calculate the energy band gap of gallium phosphide, or GaP, which is our semiconductor material. To determine the band gap, we use the formula E equals H times C over lambda. Here H is Planck's constant, 6.62 times 10 to the negative 34 joules per second. C is the speed of light, which is 3.0 times 10 to the 8 meter per second. And lambda is the wavelength of GaP's photon, giving us 549 nanometers. Substituting these values into the formula, we calculate the energy gap as 2.26 electron volts. Since gallium phosphide has an indirect band gap, it does not efficiently emit light unless doped. The emission wavelength of GaP is approximately 549 nanometers, which corresponds to green light.
So, if we wish to make our gallium sample into an N-type semiconductor, we should dope the element with silicon. Being an element in group 14, silicon will have 4 valence electrons, causing the semiconductor to become increasingly negative. To get our gallium positive, we should mix in aluminum or boron to then become a P-type semiconductor. Since these elements have fewer valence electrons than our sample, it will form holes, making it primarily positive. Now, to turn phosphorus negative, it can be combined with any group 15 element, but mainly arsenic and antimony are used, with some cases even using more phosphorus. Lastly, phosphorus is an extremely rare element to force positive. Because of its extra valence electron, it is almost always used as an N-type dopant, but it is possible to turn it into a P-type semiconductor. You would have to add an acceptor impurity like boron, aluminum, or gallium, and then force in a material like silicon to create the holes and positive charge.
In this slide, we analyze the intrinsic properties of gallium phosphide and focusing on electrons and holes. Due to gallium phosphide's large band gap of 2.26 electron volts, the intrinsic carrier concentration is very low, around 10 to the 6 per centimeter cubed at room temperature. Electrons have a mobility of approximately 110 centimeter squared per volt seconds. And in holes, they exhibit a lower mobility of 50 centimeters squared per volt seconds. Q is the elementary charge of 1.6 times 10 to the negative 19 of an electron. Using these values, the electrical conductivity sigma is calculated as the elementary charge times the carrier concentration times the mobilities of electrons plus the mobilities of holes, giving us 2.56 times 10 to the negative 9 second per centimeter. This makes the overall conductivity of gallium phosphide much more lower than materials like silicon. In summary, the lower concentration and mobility in gallium phosphide contribute to its poor conductivity as an intrinsic semiconductor.
Finally, let's talk about the application of our semiconductors in electronics and photovoltaics. Starting with gallium, this semiconductor can be used in receivers that catch microwave radiation and is also used in DVDs and compact discs. It is used in the laser diodes in these discs, as well as LED lights. This metal can be found in high-speed circuits, as well as our smartphones, computers, and other handheld electronic devices. If we look to the bottom of the slide, we can see gallium used in a computer chip for vehicle radar systems. To wrap up, it is also used very commonly in communication systems like our Wi-Fi and Bluetooth. Now, phosphorus is not commonly used in electronics, but instead primarily used to dope other semiconductors into N-types. More electronically used is black phosphorus, an extremely similar nonmetal that is commonly in the screen of televisions as well as solar panels. However, regular phosphorus is still used to speed up the injection of charge carriers in transistors, as well as fluorescent and metal halide lamps.